days, okay, which is the CRISPR was in there one by one, knocking out all 52 of these exogenous retroviruses. Needless to say, there is, I don't have a slide here, but there was big data behind this. Just like let's do this thing, nothing is sequencing a genome to get one, confirm one base pair. They found nothing is sequencing 4 pig genomes to make sure that they understood what they were getting into and to get the full collection of exogenous retroviruses and make a phylogenetic tree and decide which was the most conserved place on the virus that they wanted to attack. By the way, I didn't come up with that acronym, PERV. Okay, so here's another big data project. I think this is the last one I'll talk about. Please interrupt. This one was some major newspaper, I forgot to credit it here. I think it was Scientific American, gave this headline, which is a $100 million Apollo Project Brain. This is from IARPA, which is like DARPA, except it's the intelligence community rather than the defense community. And they wanted, they're a subset of the multiple government agencies, including the NIH and DARPA and NSF and IARPA, that are in this brain initiative that Obama announced a couple years ago and that I had some role in initiating. And I was very delighted when the acronym for this, which is the brain, included the word innovative and the word technologies, because I felt that was a good sign that we could really move the dial quite a bit. But anyway, the subset of this, which I think is one of the most innovative ones, is the IARPA subset, and they are looking for machine intelligence and cortical networks, which means that they're trying to, this is one of the rare cases where biology might be able to repay its long debt to the computational community, like many people in this room. We obviously owe a huge debt to the big iron and the software and so forth. But the idea here is that we're going to analyze a cubic millimeter of visual cortex, 3 different teams, each with about a third of that money, a cubic millimeter of visual cortex in the context of a variety of behavioral tasks which integrate all the activity in that cubic millimeter and try to come up with a code by which visual tasks are done. Because we notice that even though computer algorithms are getting pretty awesome at a variety of human-like tasks like chess, Jeopardy, and Go, those are kind of human tasks that were pretty mechanical. We just thought they were really cool because humans could do it. And so now machines are getting better at competing with humans who were competing with machines. But things like visual processing, an infant of almost any species cannot perform the algorithms today, like finding a face in a crowd of moving people. Anyway, so the idea is to produce algorithms from summarizing the data we get. And so here's the jargon here. Omics is like genomics, proteomics, and so forth. So genomics, transcriptomics, proteomics, metabolomics, microbiomics, and so forth, and immunomics. Now, this is showing you very quickly how we're doing this kind of project with a new technology that produces a ridiculous amount of data. I mean, it's going to make all you guys very, very happy. And this is called fluorescent in situ sequencing. It's something that we started working on in the 90s. I'm embarrassed to say how long it took to arrive, but it arrived in force in 2014. And forget the protocols. It gives us the 3-dimensional information about RNA. So these are 2 cells. Each of these dots is a single molecule of RNA, which you can sequence the same way. I'm sure you all know about next generation sequencing. I've been mentioning it. Normally, next generation sequencing, you would take a bunch of cells or even one cell and slat it open and split it out through a flow cell randomly, and then you get the sequence information, but you've lost track of where everything comes from. This doesn't. This says, read it where it is. It's fine where it is. We're going to harvest not just the sequence, but the 3-dimensional coordinates of the DNA, the RNA, and proteins. And I'll show you each of these in turn, each of these kinds of omics. This is RNA right here, but you can see the nucleus where there's an abundance of these transcripts. This is the instrument. We helped start most of the next-gen sequencing companies, and we collaborated with them to develop this. They each made small contributions. Mostly the device was built with Danaher's cooperation. This is kind of a data slide showing the G's, A's, C's, and C's, how cleanly separated they are, even though this is all done in situ, in cells, in place. This is these are cancer cells, so we not only provide we sell the instrument and the services, and most of the people using the services so far seem to be interested in cancer, although I frame this in terms of neurobiology. This is a summary of reads from in situ, remember this is in cells. These are like a histogram of where you can find the reads, where you can find these in the computer that matches. This is a particularly long messenger RNA, 8,000 base pairs long. And you can see there's some places that are more well represented than others, but we kind of freaked out when we saw an entire exon missing, meaning an entire piece of the protein coding region. Fortunately, in this, we went on to the second half of the experiment, and we found that what it was what's called alternative splicing, where different parts of the protein are expressed in different environmental conditions. So that's RNA still. Now let's talk about DNA. This is DNA. This is work from Sing Wu's lab. He's a colleague in our department. And this shows just how much extra data you get. You go into super resolution. So this is the data at conventional microscopy resolution with these are the scale bars here. Same image, same position where this glowing thing is overexposed. So you can see the individual single molecules here. If that is the same thing. You can see this just essentially one big blob. Here, you can blow this up further, and you can see down at the sort of tens of nanometer scale. To put that in perspective, these are individual nucleosomes at the sort of 30 nanometer scale. So you can really trace the complete folding of a chromosome the same way that we currently trace the folding of the proteins. I showed you that slide with all the rotating proteins. That's where we're going with the chromosome.
Is that still imaging technology?
What about it?
Sorry, this is saying, this is
so you could, fluorescence CT sequencing is kind of a bucket term for anything that involves fluorescent microscopy, where you get sequence identifiers that tell you where you are and what you're looking at. So firstly, you can think of all of our pathology and cell biology. In the past, we'd look at something, we might have a couple of colors, like in the past slide with the H and E stains, 2 colors, and in the cell biology, it might be 3 fluorescence. But what you really want is to know at every pixel, every voxel, what's there. And so I'm showing you a couple of different methodologies that all have the same property, which is at a particular voxel, what's there. In the previous ones, it was RNA, and these ones, it's DNA, and they're at higher resolution. So the RNA ones were all at conventional confocal resolution. These are at super resolution with full microscopy. Okay, so in that brain initiative project I said with IARPA, I said there were 3 teams. They're all using the same calcium imaging, but they're using 2 different methods for reconstructing the connectome, that is to say the synapse level connection between nerves. We might have thousands of synapses per neuron. 2 of them are using electron microscopy, and 1 of them is using fluorescence sequencing right now. Could change. The thing about electron microscopy, your question, is it has 1 color, essentially various shades of gray. And so when you look at a position in the electron microscope, no matter what kind of electron you pick, a particular category, no matter what kind it is, you can't tell what you're looking at other than by morphology. You can't say, oh, here's something that looks like a synapse. It's hard to guess whether it's excitatory or inhibitory synapse. It's hard to guess what the neurotransmitter is, and so forth. So if you have a lot of colors, then you can reuse those colors with sequencing. The trick is that you're not limited to the 4 colors that you can spectrally separate. You can reuse those 4 colors over and over. And so you have GATC in the first round. I mean, it doesn't have to be sequenced. It doesn't have to be strictly GATC, but it's a sequence of events. It's a sequence of colors. You can think of it. But typically, it is convenient that it's actually also a sequence of base pairs. Anyway, GATC in the first round, so it's one of those, let's say it's G, second round is A, T. And what happens is you get basically 4 to the N colors. So that's the difference in microscopy. I'm not saying anything bad about electron microscopy. I'm just saying that there's something really good about fluorescence microscopy because it's now getting close to the same resolution. So the cutting edge of this, which I don't think we need to go to for most of these, is about 5 nanometers. Electron microscopy, you can go down to a fraction of a nanometer, but for most purposes, you need 5, you need 50 nanometers, but you need better than conventional. Here's an example of an entire organism that's being imaged, where each of the chromosomes has its own color. You can also assign colors. You can literally assign colors to every 2 base pairs. This one is just to show, so you can see each of these cells has its own set of chromosomes right in this nice array, and you can see how the chromosomes are organized. That's relatively low resolution. So that's RNA and DNA, which is proteins, and yet another way of doing microscopy at super resolution. It's called expansion microscopy, and the previous one, the SWORM, does this at high resolution by sampling each individual fluorescent molecule multiple times. And so that takes time. You have to do that, but it gives you the centroid, which is more precise than the diffraction-limited calcium it typically would have. This is different. Instead of sampling and getting a centroid, you just literally physically expand your sample. And again, it sounds a little like science fiction, but what you do is you anchor your sample onto a hydrogel. So here's an anchor point, and this square grid, it's not really square, it's more random polymer, is polyacrylate, like what you have in disposable diapers. And you know one of the properties of polyacrylate in disposable diapers is it expands. And this does the same thing. So if you dilute it in water and remove the counter ions, it will expand up to 4-fold in each dimension. And you can do that a second time, and you get another 4.5-fold, and for a total of 8,000-fold volumetric expansion. So it makes a much bigger volume. And it's isotropic. So here's comparing 2 different, one of them expansion microscopy, the other one of the super resolution methods that just uses the physics of the optics, and you see pretty nice correlation in the size of various molecules. And, go ahead. So the question is about how quickly proteins might change in a cellular media. So this has big advantages over what I would call classical proteomics, which might be mass spectrometry. But they both, because one of the things you're doing, first of all, you're collecting in situ, so you get the 3-dimensional coordinates, you get the subtlety of who's next to who in the cell, which is lost typically in mass spectrometry. But in terms of the faithfulness of the structure at the time that you sacrificed or surgically cut out the sample, typically it's dumped immediately into either liquid nitrogen or formaldehyde, or liquid nitrogen followed by formaldehyde. And so these proteins are literally fixed in space by covalent attachment. And so all of the biochemistry and most of the chemistry is eliminated instantly. It doesn't mean that there won't be some subtle changes, and many of these we know about. And sometimes there are individual solutions for those, but for the most part, even things like protein phosphorylation state and other photosynthetic modifications are retained. Yeah, and by the way, this is proteins. So the way you do proteins is a little harder than nucleic acids. So the nucleic acids, you literally just have a computer design the probes, or you can use random probing, and then the computer interprets the sequence that you get out. Proteins, you don't have either of those tools available. What you have instead are antibodies, and so you're limited by, or you can say there's a revolution coming in these antibodies. They can either be kind of classic antibodies, these Y-shaped molecules, or they can be a smaller piece, just a so-called antibody, which is about half the size of one of these things. But you can have these antibodies which are then coupled to a nucleic acid, and this is work from Ed Williams Group, our close collaborator on many projects, including this one, where the protein is coupled to an antibody, which is coupled to a nucleic acid, essentially reducing this to a problem we've already solved, which is the nucleic acid and sequencing. So that's how we do proteins. Now, the last of the elements that I'll show you is how we do small molecules. And the way we do that is we turn the small molecule problem into a protein problem, which we've already turned into the nucleic acid problem. So you can see this little simplification, this kind of what programmers and mathematicians do is they try to reuse their code. And so what we do here is, let's say we want to detect a molecule like progesterone. We use the protein design tools I mentioned earlier that we've used on CRISPR and a whole variety of things. Here's a second example, where we use protein design tools to design a new reporter that binds to the progesterone molecule. This is done from scratch. We could go out into the wild and try to find the protein that binds to progesterone and has the properties we want, but instead we designed it. And we specifically make sure it doesn't bind to a variety of related compounds, so that other steroids, the Johnson and so forth, that look kind of similar. And so we can go through this, a combination of computer design and laboratory evolution, and we can get this nice, clear distinction between progesterone and other molecules, where the property that we get is that it is the protein, the reporter, is degraded in the absence of progesterone, and it is stabilized by progesterone. And so if the reporter is a fluorescent molecule, we can read out the fluorescence to detect this. If it's or we can detect the antibodies in the in situ assay that I showed in the previous slide. So we can turn a small molecule progesterone assay into a larger molecule protein assay via antibodies via nucleic acids. So we come back to this. The IARPA is just one of many applications of this, what we call meaning all different kinds of omics, before that showed you DNA, RNA, protein, and metabolites. But when you take it to the brain, which is what IARPA is interested in, we have activity, which for this project we're measuring with calcium imaging, behavior, which is just the contact, which is typically video data stream. So this calcium imaging data is like a video stream at as high a frequency as you can get calcium data, which is sort of on the order of 10 hertz or so, gigapixels. Video data is the input to the animal, and also what the animal is doing in behavior. And the connectome is this super resolution synapse level analysis. So you might have 86 million neurons in the mouse brain, 86 billion in the human brain. Multiply times 1,000 to get the number of synapses. It's really a remarkable number, and we're connecting this now back to the activity. We're integrating it, and then we can also collect the cell types of development. As it goes from an egg to an embryo with brain, we can trace that lineage. I'm not going to go through that unless you want to, and then we can follow expression, which is what I've been talking about so far, DNA, RNA, protein in serial sections. Now this is going to end and open it up for more discussion on a totally speculative, two totally speculative slides. There's just an indicate where just for fun. I mean, it's just playful. It could be taken as an insult to computational current silicon-based and magnetic-based computations. Anyway, here it is. Is that this 20-watt human wetware, who remained de-identified in 1905, did a number of 5 papers, which could have gotten him a Nobel Prize. In practice, he only got it for one of them. I think one of the least impressive of the papers. This task is, I think, considerably harder than Jeopardy to reproduce. Second to the slide. This is where this is an experiment I did with my own hands. Usually I prefer doing computing, but this particular case I put on the purple gloves to encode glycoproteogenesis into DNA. Some of you may have heard of this. And the idea was a very specialized form of data stores. This is not Seagate disk drive. This is on the topic of archiving. Much of it is done on disk drive. But these are about 10 to the 6 times the density in 3 dimensions, and it has the oldest DNA that's been recovered intact or readable, I should say, is 700,000 years, which is slightly better longevity record than disk drives so far. Anyway, so we have all these various would-be technologies for storing data, some of which are leading-edge physics that require liquid helium or other sources of energy. The DNA in principle doesn't require any energy for long-term storage, and we moved way up on this plot where we had information density in bits per cubic millimeter. This has all been framed, of course, to favor the new technology, and then on the x-axis is the number of bits that have been encoded in production. And of course, hard drives are way out in terms of number of bits that are stored in the world, getting into this zettabyte, yottabyte range. But this is where we're now moving our ability to encode digital information in DNA with funding from Technicolor ever since this paper came out in 2012. I'm just going to leave it at that. There's this PGN organization. I encourage you to go to this website, and we have Space Genetics website as well. So I'll just leave this open on this page for additional questions or comments or discussion, dialogue. Thanks.
I'm not from Century, I'm not part of the excuse that.
Yeah.
Thanks for them. You talked about the cost of whole genome sequencing and counselling that's available together with that genome, but at the moment, really, state of the art is a small part of the exome and the counselling around just that part of the genome. Talk about multi-omics or omni-omics, that gives you the system view. How do you see the evolution of counselling and reporting based on this multi-omics view?
Yeah. Well, so you're starting to see what I would classify as wellness and concierge medicine going up a notch by including some omics. For example, there's one in San Diego called HLI, one in Seattle called Aravel, which I'm involved in, where they are trying to integrate microbiomics, metabolomics, and genomics into a series of slightly more mature technologies like whole body imaging and so forth. Now, some of these have raised concern in the past just because of over-diagnosing and hypochondria and so forth. But if you treat it as baseline, where you're getting information on a healthy individual and you're not acting on it, and then when something happens, so rather than saying, oh, I got an incidentaloma, I saw a little blurry white patch in my abdomen, so I'm going to do exploratory surgery, instead you just say, I'm just going to watch that, see, and when I ever do develop a serious medical symptom, I'm going to see what the baseline imaging look like, or the baseline genome look like. That said, and when you do have a symptom that locates a particular part of your body that you want to sample, you'd like to do that with the best tools that are available. Each of these things, whether the therapeutics or diagnostics, are going to have to go through the usual process of safety and efficacy testing, and try to minimize the false positives relative to current practice. There are two questions. One is having to do the reference genome, being kind of a half and a mixed genome, and the other is each new genome coming in that's of relevance to you. How should that be done from scratch? That's what I got out of the question. So the reference genome is already evolving into not just a half genome, it's a mixture, kind of a monster, to a series of diploid genomes. And in fact, part of this is through a new standard setting, which your agency, the FDA, and the National Institute of Standards and Technology, NIST FDA, called the genome model, where they're taking trios, meaning mother, father, and child, multiple, I think 8 different trios, most of which come from the Personal Genome Project so far. And now using those to say, at this position, this is the kinds of copy numbers that we see. Right? In other words, I'm not just going to pick one of them, say from your mother. We're going to pick 24 times 2 at that position. And that will give us a population idea of what can happen there in healthy individuals, although nobody is absolutely truly healthy. But anyway, you start accumulating this information, and that's the reference. And then for each person, if you assemble their genome from short reads based on the reference, even a better reference that involves 24 people, you can make a mistake because you're kind of assuming that the scaffolding is right, and it could be this person came from Mars or Neanderthal or something, and the scaffolding is not right. And I should add to that the reference genome, even with 24 really well-done genomes, no human genome has ever been complete, which is another warning about the scaffold. I think that's going to change in the next year or so. I think in situ sequencing is the first method where you literally have connection between telomere to telomere, all untouched. You haven't broken it up into pieces at all. It's the biggest piece you can possibly get. Some of these chromosomes are 250 million base pairs long, and the pathetic little Illumina reads are still 300 base pairs long. So I think assembly is a problem, and for the time being, we'll do the best we can. We can do de novo analysis now, but I think in a year or two, de novo sequencing, we're going to laugh that we ever thought that was challenging. That's my full prediction. Yeah, David and I are close friends for many decades. But I would say my version of it is a slightly more extreme version of open, and we have 10 years of experience with it. So the first paper we published on Personal Genome Project was in 2005. In this version, we interact with the individual rather than with large data collection groups. We interact with the individual. We enable them to know what's going on with their own data, so they're not treated like a lab animal, which has no rights. And we also enable them to share it, first making sure that they know what they're getting into when they share it. So a lot of the sharing that's going on right now is with patient samples where the patients don't really know what that means. They are unaware how many instances of even private data are breached that are released. They should know because of WikiLeaks and other things are very prominent. 26 million veteran records. Almost every hospital has been broken into at some point or another. And they should know this, but they don't. In fact, the value of medical records now is higher on the black market than credit cards by a factor of 20. And you might wonder why I know this, but anyway, I know this. And I'm not selling anything on the black market, it's more buying. And the reason is because the credit card you cancel right away, it's ephemeral, while the data that's in your medical records is permanent and for some reason they're used as identifiers. your social security number, your mother's maiden name, your eye color, height, weight, so forth. These are permanent, relatively credit card anyway. So they should know that things get out and that things get re-identified. If you have a risk data set, which is almost every useful medical data set is now rich, being identifiable. So anyway, so those are the two things we make very clear. And most studies have you to sign a 10-page document that says that really is written by a lawyer or lawyers to protect the institution.